Hi, so in this video I want to amplify a little more on the subject of Z-transform. I feel in the lecture they kind of just drop this on you without really giving enough to understand the context and what's going on with this. Now, Z-transform is the first example that we're going to see in this class of a transform, which I can say is a transformational concept. No pun intended. It's really a key idea in signal processing and in math in general is to take some object and represent it in a different way to gain some insight. So here we're going to look at Z-transforms. We're also going to look at Laplace transforms, Fourier transforms, and all of these give us different insight into the structure of signals. All right, so let's begin with Z-transform. Z-transform is a transform of discrete signals. And we saw the idea of a system functional. The system functional tells you how the system responds to an impulse. I have an example of a system functional down here. What this says is that if I put an impulse into the system, then what comes out immediately is a 1. So you know, an impulse is just a signal of 1 that's momentary. So if I put a 1 in the signal, then 1 comes out. But then at the next time, after one time clock or one time delay, a signal of 1/3 comes out, and then 1/3 squared, and so on. So you get this decaying response through the system. All right. So that's the system functional. Now, there's this mathematical operation you can do by simply replacing the R in the simple functional, in the system functional, with a 1 over Z, or 1 over Z if you're in Canada. So, alternatively, when the Z-transform is expanded in powers of 1 over Z, then the coefficient of 1 over Z to the n, or Z to the minus n, is the impulse response at time n, right? So the Z-transform of this system down here, you just replace the R with a 1 over Z, or Z to the minus 1. Now, one question that's fair to ask is, why make it so complicated? Why replace it with 1 over Z? If you're just doing an algebraic variable, why not just Z? And there are various reasons for that. But I think it has something to do with the fact that if you use 1 over Z, then the pole of the function, that is the location where the function blows up, corresponds to the decay rate. Right here, the decay rate is 1/3 because you're going down by 1/3 each time. So if I use 1 over Z, then the pole of the function turns out to be 1/3. So that it makes the poles very easy to interpret. Okay, so as I said, here's a signal that decays at geometric rate 1/3. Here is the system functional, the Z-transform. You replace the 1/3 with a 1 over Z, and you get this here. And of course, you can expand this out. This is going to be if you write it this way, it's well. You could. I don't think I need to. You just get 1 plus 1/3 times 1 over Z plus 1/3 squared times 1 over Z squared, etc., etc. And naturally, this series is going to converge if this term here, this geometric term, has absolute value less than 1. And that means that Z is greater than 1/3. You can work that out. If the reciprocal is small, then the value is large. So, what's the meaning of this Z? What's going on with this Z? So, neither the lecture nor the book say much about this. They just treat it as a mathematical device. And in fact, it is in some way a mathematical convenience. When we do Fourier transforms, we'll see that the variable has a physical interpretation. But here, you can come up with some kind of interpretation. So think of it this way. So remember that R in the system functional represents the delay between the original signal and the feedback. Okay. Suppose the system is modified such that every time the signal is delayed, it's also divided by Z. Okay, so you can say that there's a suppression factor or something, and z is the suppression factor. All right, now if z is less than 1, that suppression factor is going to be an amplification factor. Okay, so suppose when the signal is delayed, it's also amplified. I could say amplified by 1 over z. Then z is in the convergence region if and only if the impulse response of the new system does not blow up. All right? So in other words, if you delay and amplify and the system still doesn't blow up, then that z is in the convergent region. Now, this means that the larger values of c, the more likely it is to converge, because the amplification factor is 1 over z. That's the same thing as saying the suppression factor is z. If you have a larger suppression factor, then you're more likely to get a system whose response decays with time. All right, so let's go back to this system with this functional 1 over 1 minus 1/3 times r. If z is 0.5, then replacing r with r over 0.5. Now remember what that means. That every time you delay the signal in the system, you also add this block of 1 over 1.5. So, in fact, you're multiplying. That's the same thing as multiplying the signal by 2. All right, so that changes the response, and instead of the 1/3, you get 2/3. But this still dies out over time, right? Because 2/3 to the n, when n gets large, still goes to 0. So z equals 0.5 is in the convergence region. But if z is 0.25, then you'll see that the amplification factor in this case is 1 over 0.25 or 4. And that if you're amplifying by 4 each time, then this signal is actually blowing up. Okay, so z equals 0.25 is not in the convergent region. Okay. Of course, this division by z is somewhat artificial. It's not something that you'd actually do in the system. Really, for our purpose, the important thing is that z equals 1 is in the convergence region, because this gives the actual system response. If z equals 1 is in the convergence region, then the signal will die out over time. Signal dying out over time is the same thing as saying that the sum converges, because in this case, if it dies out over time, since it's a geometric series, the geometric series will converge. Okay, all right. Now, it's possible that if z equals 1 is not in the convergence region, that means the impulse response does not vanish over time. However, it's possible that the backward signal does vanish in time. Now, you got this backward signal, which is really kind of weird. But I'll say more about this also in the next video. But just bear with me. So if you have a system functional of 1 over 1 minus 3r, okay, then the z transform is 1 over 1 minus 3. Replace the r with 1 over z. And if you expand that out, you get 1 plus 3z inverse plus 9z to the minus 2, right? So I'm just using the geometric series on this. So these coefficients are getting bigger and bigger. Obviously, this system is growing. It's not dying out. On the other hand, we could expand the z transform in powers of z instead of powers of z inverse, right? So you can use z as your expansion variable. Now, the easiest way to do that is to reformulate this expression so that it looks like a geometric series in z. So here I kind of massage this around, so instead of 1 over z, I got a z. This is not in the geometric series form, but if I divide by minus 3 and take out a z, I get minus z over 3, 1 over 1 minus z over 3. So 1 over 1 minus z over 3, you can recognize this as the infinite geometric series. And that's 1 plus z over 3 plus z over 3 squared plus z over 3 cubed, etc. So I can expand out what is inside this parenthesis as a geometric series. Then I multiply it by minus z over 3, and I'll get this series out. Right? So here we have powers of z, and the powers of z are multiplying exponentially decreasing coefficients. Okay. Right. Now remember that 1 over z represented a system delay. So we can interpret z as representing a signal advance. And this becomes a signal in past time that starts out small and negative and eventually reaches a value of minus 3 minus 1/3 before it gets suppressed. So I'll say more about this in the next video. But again, this idea of generating a signal backwards in time is kind of weird, but you can see how this system functional can be made to correspond to a signal backwards in time. Okay? All right, so think about that, and we'll continue on this same topic in the next video.